So we're talking about homothety in this class, so we'll go over some basic like first definitions and then possibly Simonji's theorem and do a lot of problems. Okay, so first let's just see the definition of a homothety. So homothety is a transformation. So you take a center of a homothety, which is P, and then for any point A in the plane, you send it to the point B such that PA over PB is equal to some fixed constant K. So the way you should think about this is just like you're looking at the whole plane through P and scaling it by a factor of K. And so usually like all sort of geometric things are preserved when you scale the whole thing over. So this also preserves most of the things which you would expect it to preserve. So for instance, we can look at a line in general, and if we project it through, not project, sorry, if we take a homothety through P, and then this point A goes to A prime, and we have another point B which goes to B prime. So then this line is in fact, and then so the point that is that a line goes to another line. So if we take this and the image of this, then these two will also be collinear. So it preserves most of the geometric properties, and okay, in fact, it also preserves direction. So look at this. I mean, that's just similarity. Like this angle is equal, and yeah, this angle is equal, and the ratio is the same. So you can use BPT or something to just get that AB is parallel to A prime B prime. Does the definition make sense? I will take that as a yes. So yeah, like I said, it preserves all the geometric properties. So it will also preserve circles and everything. So if you take a circle and you take a homothety, then it will go to another circle. In particular, if you have a circle through the center itself, this is not a great circle. Okay. And then if you take a homothety, so then it will go to another circle. But so it goes, okay, so under homothety, you can see that the point P goes to itself because, okay, this is not the best way to write it in this context. You should write as PB equals K times PA for it to make more sense. And then PA is just 0 if A is equal to 1. So P should map to itself. So now this circle, look at the image of this circle. If it's something like this, then what does that mean? That's the point Q. Is something like this possible?
No, it would be tangent to the original circle.
Yes, that is true. So if it were to intersect at any other point, then we would take PQ and look at the homothety. So, okay. So Q lies on the small circle. So it's coming from like some point on the big circle. Right? So you take like the reverse homothety if this is omega 1 and this is omega 2. So then this thing, you can obviously reverse the process. This, you can reverse the homothety and it's still a homothety. So you look at the homothety taking omega 2 back to omega 1. And no, wait, never mind. You take the homothety taking omega 1 to omega 2, and then it will go someplace outside because like a line can only intersect the circle twice. So we'll get tangent circles. And there are a lot of nice things. Okay. So now we can use homothety to prove some basic things. So first let's prove 9-point circle. I mean, we'll only prove like 6 points because the other two are not that great. But the other two also follow directly. The other three, I mean. We have DF as the feet, and M and P are midpoints of the three sides. So then the 9-point circle is a circle passing through these 6 points. We have to prove that these points lie on a circle. Yeah, and yeah, so the way we prove this is by taking a homothety at H. So this circle, okay, it's not just a random circle. One other nice property about the circle is that it has radius r by 2, where r is the radius of the big circle, of the circumcircle. So this is in fact the image of the circumcircle of ABC if we take a homothety at H with ratio 1 by 2. And we can see that because, so, no. So if we take the reflection of H over D, that also lies on the circle. Okay, you should not really think about it as a reflection in this context. You should think about it as a homothety from H, but it also happens to be a reflection. And okay, how do we prove this? That the image of the homothety lies on the circumcircle.
Which points are you referring to?
I'm referring to the feet right now.
Like we need to prove that D dash lies on the circumcircle of ABC.
Yeah. Okay. For now, just take D dash to be the intersection, and then we have to prove HD equal D dash.
Okay, we can prove it using angle chasing.
Okay.
Uh, yeah, we know that angle HD dash A will be equals to angle C, and we know
D
that
dash A
angle
is not okay. HD dash B is equal to A. Yes. No, it's
we
equal to C.
know,
Sorry.
yeah, and C. And
Okay.
similarly, like we know that angle EBC is like 90 minus C,
Okay. Yes.
and this
Exactly.
triangle is 90 HDB is 90 triangle, so BHD is also angle C.
Yes. Exactly. So it's just reflected to it. So we get the feet of altitude like that, and then what do we do for the midpoints?
You can like prove if you take a homothety as ratio 2, it goes to the circle.
The circumcircle.
Like it, like you could like consider the um you could consider the point where HM intersections, or like you could just make like consider the reflection of H about BC.
Okay.
And okay, yeah.
About
And
BC
like
is D dash. We need to consider it over M.
yeah,
Okay.
yeah, fine. Yeah, it's the same thing. And then this means that angle BM prime C is equal to angle BHC.
Okay. Exactly. Yes. And angle BHC is equal to 180 minus 6. So, yeah, then. Okay. So that gives us that, and it also gives us a bit of additional info. So when we take a homothety, here we'll just take the point P to be outside the circle. Like we take a circle and its image. So then another nice property is because homothety preserves all the geometric structure, it also preserves centers. So what that means is that if O2 is the center of omega 2, then O1 will be the center where like O1, then the center of omega 1 will be the image of O2 in the same homothety. And okay, so we can prove this formally, but like intuitively does it make sense because it should preserve all the geometric structure.
Yes.
Yes, okay. Yeah, formal proof is just, it's fine. We'll not worry about the formal. So yeah, this we get this 6 points. Okay, actually the 9 points, the other 3 points are just trivial. So we look at the image of A, B, and C under this, which are the midpoints of AH, BH, and HC. And those are the 9 points on the 9-point circle. Okay. Okay. So these are, you can do this, and then also homothety can be used to prove Euler line. It's okay, I'll do that as well. These are the details. So yeah, I'm not really drawing everything. Edge. Okay, right. So we need to prove that GHO are collinear and GH by GO is equal to 2. Yeah, it's equal to 2. Or I mean, you can look at it as -2 if you want to think about it as direct inlets, which is what we use for homothety. So like we can do this, and we can also take a negative homothety, which is like we take B to be on the opposite side. Yeah. So do you have any ideas for this?
We can use the fact that like centroid divides it median in the ratio 2:1. So we could take a homothety at G with ratio -half.
Minus half. Yes, exactly. So under that homothety, ABC will go to DEF.
Yes.
Okay. Right, and what we want to show is that H goes to O.
Yes, that's just basically like O is the ortho center of DEF, which is
Exactly.
because EF is parallel to BC and DO is perpendicular to BC.
Yes, that is exactly the proof. So O is the orthocenter of H of DEF. H comes to. That's it. Right, so that's like a really intuitive proof of Euler line. I think there are some others using aliens, but this one I find really intuitive. Okay, there's one more problem. Okay, so let's do one more slightly harder problem, and then we can look at some theory. I will draw a diagram, but I would highly recommend drawing your own diagrams because my diagrams are not great. The weird waste. Sim. No. Some zero conditions. And what we want to show is that these points are like yeah, so I mean you have parallel lines and like this is a homothety class. So what we are going to do is extend the parallel lines to meet somewhere. Is at x, and what we get is that there's a homothety at x with some ratio, it doesn't matter, which sends DC to AB. In particular, it sends D to A and C to B. Okay, so, and also we have a weird condition on these things, but it's just saying that AK by KB is equal to DL by LC. So, and like that's also directed length. So the image of K should also divide DC in the same ratio. So L should be the image of K. Because I mean it's also there are some configurations like L could be outside, but we are given that it's on the side. So it's all good. So we get that K passes through X. Does this stuff make sense?
Yeah, probably we can now look at where P goes.
P. Okay, right, yes. That is true. That's a great idea. So P will also lie on the segment. And we can suppose it goes somewhere over here. Some people. Okay, so what do you see? There's okay, do you see any cyclicity? We can change angles using these parallel lines.
P dash DKC is concyclic.
Exactly. Yes.
And like also draw point Q for simplicity.
Oh, point Q. Oh, I've not labeled it. That is true. Wait, did you want to draw the image of Q? Until I mean, okay, sure, we can add the image of Q. But then that would be a slightly weird point. So we'll have to look at the image of CD and then get the angle condition. So good idea, but since the conditions on Q are using CD itself, it would not make that much sense because we'll have to introduce new lines. Right, so what else do we have? Okay, so let's also think a bit about what we are supposed to prove. We need to prove PQ, CB are cyclic. So how can we prove something like that? In this figure. Like, would you like to use some specific angles and show that they're equal or something else? Introduce points.
We need to show that we can perhaps show that
Mm.
APK is equals to DCQ, then it might lead to showing us that the triangles are similar. I'm not
Mm.
sure.
APK is okay, interesting. How does that finish? And how does that help with proving the cyclicity?
Like we need to prove that angle KPB is equals to angle QCB. So from there we can like backtrack things.
Yes, that is so. We're gonna get APK versus TPK. Okay, that's a different proof, but that's also great. So that's not the finish I had in mind. Okay. So yeah, APK is here and we can also take a homothety. And homothety preserves lines, so lines map to parallel lines. And so it also preserves angles.
I think then we also have that the circle we just shown CQDP dash is tangent to XP.
Yes, yes, yes. So that leads to a different solution, which is the one I had in mind. Okay, so I'll mention both. So this is angle APK is in fact equal to this angle because we take a homothety at H and A maps to D, P maps to P prime. And what is the other angle? DCQ. That's just this. So this equality is true because of the cyclicity.
Wait, like did you also backtrack or did you just prove it?
I backtracked and it worked. Okay, I'll do it in the forward direction. So we have dpq equal to dcq, and then like dp prime q equal to dcq. So then for dp prime q, we can take a homothety at x.
Oh yeah,
And
okay.
then we know that these two lines are parallel. So we get that angle APK is equal to angle DCQ. And since
Yeah,
these
got
two
it.
lines are equal, this are equal to this. Yes. So the other solution is that you can note that this angle is equal to this angle. So BC is tangent to that circle. Yeah. Now to prove this concyclicity, we can also use power of point because like these two lines meet at a really nice point, which is X, and it's the center of our homothety. So we can use that. So into XP into XQ. How would we go about proving this? Keeping the homothety. Like how can we use the homothety to understand this?
Wait, X is the intersection of CQ and TB.
No, X is this point. BC and AD and KR.
Oh, sorry.
Yeah, so X is also like homothety sending DB prime Q C to A, P, B. Because they're parallel. Yes, so okay, let the ratio of homothety be K for convenience. So how can we use K over here? Okay. Okay, so one thing is that XP and XB, we can both scale by the same factor. And then like this will be equivalent. So instead of XP, if we can consider XP prime times XQ equal to XC times, where does B go? B goes to C. So XP. So like XP prime is just equal to KXP. So that makes sense. XC. And XC is equal to KXP. So this is equivalent to XP prime times XQ equal to C square. And that is true by power of point. Okay. Are there any questions about the game?
Can I tell my solution?
Yes, sure. What's your
QP dash C is equal to QDC.
QB dash? Wait, can you repeat?
QP dash C
Okay, QP dash C is equal to QDC. Yes.
and is also equal to QPB.
Also equal to QPB. Why? Okay, yes, because of the homothety.
And QDC is equal to QCB.
QDC is equal to QCB because of the tangency. Yes. Okay, yeah, so we are done. That is a bit similar in essence to like this proof, but it's a different way to go about the angle chess. It's like the idea of computing angles by taking homothety, and that's kind of similar. Okay, so yeah, this idea of looking at power of point and how it changes with homothety, it's actually a really common idea. So, like the equation in power of point is like PA times PB equals PC times PD. And if you think about it, that is kind of similar to, okay, it's not really, but what we would have for homothety would be something of this form. So we can understand power of point by using homothety. That is also possible. In
How
a
is the
second,
second thing true?
which second thing?
Like the thing you just put right now. PA by PB is equal.
Oh, this is not, okay, it's not this. It's, so it's actually PA by PC equals PD by PB. I was talking more of the general, like the form of what the equation looks like.
Okay.
So yeah, this, okay, I will do this now. I was trying to get to this slightly later, but we can do it now. That's fine. Yeah. So this condition is Okay, it's a little weird because the lines are mapping. It does satisfy this ratio, but the lines are getting like C does not lie on P. Maybe if you take C prime over here, which is the corresponding points, is that this is isosceles, then C prime would be the image of A under a homothety. In particular, what you can do is take take PAC, take PAC, and then first do a homothety of some ratio. Let's do a homothety, and then reflect about the angle bisector. The idea behind this is just that you want to swap these two lines. So reflect about the angle bisector of angle APD. So then what happens if you do this? Okay.
We can take the ratio as such that okay, we are not taking it.
Yeah, we can. So we can choose the ratio for the homothety, and
Yeah.
yeah, we can choose it in a way that this thing goes to this PSC, so PTB. And that is like a nice way to think about what it means for 4 points to be consecutive. You can introduce this P, or you can look at this point and a similar condition holds. Because, yeah, it holds by the same logic. So this is, it's a common theme in problems. You can do this, and also what we used over here is in this problem, the idea behind the power of point, like and the idea behind the power of point argument was if you take a circle and you have these things like you have A, B, C, D, and you take a homothety at P and just look at the images of A and B, A prime and B prime, then these 4 points will also be cyclic, which is what we used in this problem. So we had P prime Q, C, and C cyclic because it's tangency. And what we did was we took P prime and one of the C's and homothety both of them. So P prime went to P and C went to B. And we got PQBC cycle. This is a common theme we'll be seeing in problems. Keep this in mind. It's in fact really useful in certain configs. So for instance, if you're looking at the author center config, then again let's do the problem first. It will seem a bit random because it won't seem that random. It's fine. Keep this. What a nice title. Let's just pick Q. And then we take the C median, which is the reflection of the median about the angle bisector, which is, it actually has some great properties. And what we need to show is that, so like let the median intersect EF at K. And the point is that KP, which seems like a very random line, is perpendicular to BC. Give you a few minutes to think about this.
Is this joined now? So can you did you do anything very important in the last 30 minutes? I'm familiar with homothety and also did you just do the basics till now?
Yes, I just spoke about the basics, and how homothety relates to power of one. So
Okay, okay.
like you can look at it as homothety plus reflection about the angle percent. Like this. Yeah.
That's it.
Um,
Are we trying to prove?
So we are trying to prove that if K is the intersection of AM and EF, and P is the intersection of the median with BC, then KP is perpendicular to BC.
Okay.
Maybe sometime. Do you have any ideas? Well, I mean, we have this circle which I have drawn, and we have both the intersections marked and really nice. So you can think about like we'll be it
Homothetics
is
center
completed
being
with it.
A, kind of.
What?
Homothetic center being A of some of this circle mapping to something like.
Yes, fair enough.
So, your median AP is passing through the ortho center in this diagram.
Oh, that is true. That is not supposed to happen. Sorry.
It's a bit weird.
Yes, it is a terrible thing to happen. I agree. What should I change?
What's E there?
E is the foot of altitude from B.
Then like how is okay?
This is not exactly straight, but it is not passing through it, so it's fine.
Yes,
Um,
that is why I was confused.
okay, just like believe me, it does not pass through H. They're different. I know this is a scuff diagram.
Shouldn't KP go from H?
KP does not pass through H because um, then this would have to be the foot of altitude from
Then
A.
Oh
K,
yes,
KH were like collinear stuff.
yes,
Oh
yes.
yes, yes,
So
that would.
it was the same.
Yeah, I will actually make a better diagram. So yeah, we should think about doing something from A only. This does not look true, but KP is indeed perpendicular. And these are totally equivalent. It's fine. So yeah, we need to look at some homothety at A. And we can do two things in this configuration. So we can either take, I mean, we have to do homothety plus a reflection about the angle bias. So we can, in the previous example, what we did was we took FC to EB, we can do that. Or we also have the option to take FE and map it to BC. No, to CB. So you can do both of these things. In this case, I guess this looks slightly better because we are dealing with the line EF in this problem a lot. So this intersection otherwise seems a bit random. So we will be taking this homothety because
Are
like
you
FC we
saying
don't
that
really care.
K maps to B somehow
K maps to P. Okay.
after reflecting?
Okay, so that is true because
Wait,
the line AM will go to the line AP because we are reflecting about the angle bisector. It's not just the homothety.
Homothety and the reflection.
Yeah, we are taking both. That's Yeah, if it were to be a homothety, then this would be like EF and BC would have to be parallel. Okay, so then yeah, that is true. So K will like line AK will go to AP because we are reflecting, and then K will go to P because EF goes to BC. So like K lies on EF, so the image of K should lie on BC. So how
Yeah.
did you finish from here? Equals to P. Okay, what do you think happens to M? Like, okay, if we look at the inverse homothety and
It goes
reflection.
to like intersection of AP and FE.
Yes, that is true. That will go to this point. And so what do we get to know about this point? By homothety things. Don't look at the data. Like, don't trust the data too
Midpoint
much.
of EF, right?
Yes, exactly. So it preserves normal things, so it also preserves midpoints. So N is the midpoint of EF, which is not very true, but it is, which doesn't look very true, but it's fine. Okay. There we are, 31 sizes.
So if we show AK perpendicular to EF, we would be done.
AK perpendicular to EF.
Yeah.
I don't think that's true. But how do you finish from there?
I was
If AK is perpendicular to AF, then AP would pass through the orthocenter.
That is true. Yes.
That's like special case. So
right.
Yeah.
Oh, got it. Yeah.
Yeah. AO is perpendicular to EF. AM is not. Okay. So
That
from
is
this,
not true. Like, if it is perpendicular, it need not pass through the orthocenter. Like, we need to pass through orthocenter, it must be collinear, and it is not necessary that AKH is 90 degree. Sorry, AKF is 90. Like,
AK. No, but
I'm saying that
no, what?
to pass through AH,
What?
to lie K on AH, it
Hmm.
is not necessary that it should be 90.
It is right. Sorry.
K maps to Q under the homothety. Okay, and if you have a perpendicular, which is if P is the foot of the perpendicular from A to BC, then it will pass through the orthocenter.
Hmm.
Okay, you are talking with him already. Sorry.
So yeah, we have this, which is kind of similar to what we had for. So now we have this thing which takes NK to MP, and this is a homothety plus a reflection about the angle bisector of angle BAC. But because of these angles, we have that the angle bisector of BAC is same as the angle bisector of PAM. So this transformation is actually really nice. What does it give you?
Can you actually angle chase in this?
Angle chase. Oh,
Like,
uh,
does this not give K and PM cyclic crossover?
yes, exactly. It gives K and PM cyclic. In fact, okay, you don't really need to do what I just said, but yeah, that's the main point.
So now we are left to prove that MNP is 90.
That's easy because n is the midpoint of EF. So like NF equals NE and MF equals ME. So MN is the perpendicular bisector of F.
Yeah, that's the idea.
Yeah.
Nice. Okay. So yeah, I'll just repeat how we got the cyclicity. So K goes to P is just saying that A. So the reflection about the angle bisector doesn't really change the length. So K goes to P implies that AK by AP is like the ratio. So AK by AP is equal to AN by AM. And then if we multiply it out, like to cross multiply AK times AM is equal to AN times AP. And so by power of point, we get that these are cyclic. So now we just need to prove that we have that MNK is equal to, no, MPK is equal to MNK. So we need to prove MNK is equal to 90. And N is the midpoint of EF. So that is equivalent to saying that M equal to M. And that is true because both of these are in fact equal to M, B, and C. Like this is a right angle triangle and we're looking at the midpoint, which is the center of the whole circle.
Can you repeat what you said?
Yeah. Okay. So N is the midpoint of EF and wait, what? Yeah, so ME is equal to MF because this thing is the circle with diameter BC because these are all 90s. So ME is equal to MF and so M and like the foot from M onto EF would be the midpoint of EF. Which is um what is going on? Okay, yeah, E is the foot from B onto AC.
It's quite hard to see with the bad diagram.
Yes, that is true. I mean the perpendiculars are not that bad. It's just the AP which was
It's just the fake perpendiculars is the issue.
yeah, true. You should not depend on my diagrams. Like you would not have guessed any of the midpoint of EF from this diagram. Um okay. So now for the sake of like okay, because of popular demand, we will look at complex numbers and how this looks in complex. We won't be like properly bashing. We'll just see what it looks like. You don't need to know any complex bash. You can also skip this part. It's fine. Okay, so if we look at a homothety on the complex plane, then okay, let's say for now that the center of the homothety is at the origin. Then we have this. And then what the homothety would look like is just we're just scaling it. So that's just multiplication by a constant real number. Right, so homothety at the center is of this form. Homothety at O. And O looks like this. So how do we find what it looks like in general? We just want to understand the structure and like how they relate to each other. We will not be complex bashing because yeah, this is not a complex bash class. So we have what it looks like for when it's centered at the origin, but say it's centered at some other random point B. So we want to send A to B. And again, like the ratio is some real number R. There is demand. Okay, there is no demand for complex bash. That is good to know, guys. It's good to know. Um, okay, so to calculate this, if we can do it for the origin, then this is like a geometric property, so it should translate nicely in some sense. So what we will do is PA by PB. So that's the homothety. And if we have this, then we can translate the whole figure on the complex plane. So it's that like instead of P being here, P is just at the origin. So what we'll get is that we'll get this point P prime, which is equal to O. And then we have A, but A instead goes to A minus P because we are translating the whole thing by a factor of P and sending P to the origin, not a factor of P, translating it by P. And then B will go to B minus P. So what happens here? So now we can look at it as a normal homothety at the origin. And so like B minus P is equal to R times A minus P. Again, terrible diagram. These two are not in the same direction, but it's fine. So this just gives us that B is equal to RA minus RP plus P. B is like f of A, the image of A. So more generally, a homothety is a function of the form which sends x to, it's a linear function. And okay, it's not just, okay, it's a linear function with R being a real number. This is the ratio of the homothety. This somewhat makes sense. It's fine if it does not. Like you don't need to know complex properly. There's just some intuition to see how it would relate. So now we know that a homothety is a linear function. So what can we use that for? We can, okay, so the point is that if you have two linear functions, then we can compose them and get another linear function. Which it's a bit hard to see, I guess. It's more intuitive this way, I guess, than seeing it synthetically completely. So we can compose linear functions. And the ratios just multiply.
I mean, this translates to saying that composing two homotheties is a homothety itself, right?
Yes, exactly. So composition of two homotheties is a homothety.
Like the three centers will also be collinear, right? I believe
Yes.
it will be.
How do you prove that?
I mean, you can use Mendel's, I think. Yeah.
I mean, it should be true by symmetry. Like everything is symmetric about that language. But we can also just prove it with homothety stuff. So if you have homothety at A with ratio R1 and a homothety at B with ratio R2, and then they compose to form a homothety at C with ratio R1, R2, then how do you show this? Like we can just look at some points and see what happens. So for instance, if you look at A, then so we're looking at like homothety at A composed with homothety at B is the homothety at C. So if we apply this at A, then we'll get like FC of A is equal to FA of A. So the reason we are looking at A is that A is just extremely nice for looking at homothety. Like for the first homothety just becomes trivial if we are doing it over here. This is like FB of A. So whatever it is, it lies somewhere on this line. Right? And we also have that C A prime A need to be collinear because this thing is a homothety at C. So C also lies on this line. It's fine. So ABC are connected. Does this make sense? Okay, I'll take that as yes. Let's see. Okay, so fine, let's do an. Okay, do you want to see Monge's theorem? We can quickly do Monge's theorem now, or do you want to do a problem? We can do Monge's theorem next time.
Wait, wasn't Monge's theorem just this thing?
Oh, it's not exactly that. It's the statement for some circles.
I mean, yeah,
Like
look at
The composition of homotheties is a homothety section.
yeah, that's the only main idea behind Monge's theorem.
Like that external tangents thing, right?
Yes, yes. External tangents, and you can also do it for internal tangents. So it will be slightly different because internal tangents give you a negative homothety. And then so should we do Monge's theorem, or there's another very nice problem which I want to do based on this? We can do that as well.
can do a problem. You can do the theorem anytime you like. It's very
Right, I didn't get you. What?
the theorem's pretty standard, right? If you want to look at it.
Okay, I can put it on homework.
Yeah, we should do the problem.
Yes. Okay, let me paste the problem. Yes. Okay, this is the statement. I shall try to draw a diagram, but draw your own diagrams preferably. Okay. Maybe see here.
Just a note, you've drawn DNA as points and that may cause problems later.
They look like midpoints, yes. Let's not do that. And it's fine though. It's not very bad in this case. But yeah, we should not do that. This is Q. It would have been better to first draw the lines and then mark X as the intersection. Okay, and now we have these two circles. They intersect somewhere at Y. We need to prove A, X, Y collinear. Copy. It's fine. We will work with this. I don't know why it's not copy pasting. Okay, so we need to prove AX, Y collinear. So first of all, that is just like ax y collinear is terrible condition where y is the second intersection of these two circles.
We
That's
can
just
do
saying that A is on the radical axis.
I guess we don't even need homothety for this. This is like POP and languages in that.
There is a POP and angle chase solution, but then you have to do some very complicated stuff. Okay, not very complicated, but you need to introduce new points, I think.
Yeah, indeed.
Indeed, yes. That is there.
Can we
I
like
mean, the solution I came up with used homothety.
can we omit the circles like the circles are so bad as you said?
I agree.
A
Yes.
is the radical axis.
Yes.
A lies in the radical axis.
I would never have drawn the circles.
We can try to show the powers are equal.
Yeah.
Mhm. Okay, yeah.
Okay, let's just not. So yeah, we have a lot of parallel lines, and we should do homotheties. Homotheties are good for that. And these are two natural homotheties to consider because of the intersections. Do we do?
First one looks better.
It does. But then P and Q are quite random. Like you wouldn't know what to do with P and Q. And think about all the stuff we've done so far.
There is actually a simple solution to this with similarity.
Okay. Sure, let's hear it.
It is just no, don't believe him. It is just so non-intuitive. It just comes out with random stuff.
For me,
Okay. Sure. Okay. What is it though? Like, is it very complicated?
no, it's like one line.
Okay. Okay. What's the similarity?
It's not exactly similarity, it's like more like BPT. Like
Yeah.
you let AX intersect BC at Z and you
You're
let
doing homothety. Okay. Sorry. Sorry. Go on.
okay, yeah, that's basically homothety, yeah. But like I did not use that concept. So it
Okay.
intersects at Z and it intersects DE at Z prime.
Okay.
Um, one sec. I'll just wake up one sec.
Exactly my point. The introduction of these 2 points was the Indian duty.
Okay. We should still like look at this. Z is anyway a nice point to consider because we want to show AX is the radical axis. So we don't have to deal with A specifically. Like we already know X lies on the radical axis. So we can take Z or Z prime and look at Z because Z has these. Z
Yeah.
has BC has so many points on it. So I need to prove that CB times ZQ is equal to ZP times ZC.
Yes, and this is actually very simple. Like
It is indeed.
ZB by ZC is equal to Z prime D by Z prime E, right?
Yes.
And that is equal to ZP by ZQ.
Oh, okay. That is homothety. You've done the entire homothety.
Okay, yeah, like I guess like it is. I mean, I use similarity. I didn't even think about homothety.
Homothety is similarity. It's
Yes, yes, but I
uh,
didn't even think about homothety.
Yeah, fair enough. Okay, so the idea is like any one of these individually will not do the job. We need to compose these two homotheties. We have
Yeah.
so we have HA and HX, let's say. No. Okay, HA sends BC to D. So then B goes to P and then C goes to Q. So the center of this homothety, so like the line BC is preserved. So where does the center of the homothety need to lie?
On BC.
Yes, exactly. It lies on BC and is the composition of these two homotheties. So it needs to be center. So it needs to lie on AX also.
Oh, it's Z. Okay.
Yes. So that just finishes.
Oh God.
It's nice. I like it. It's a bit scam, I suppose.
Wait. Why does it need to lie on X?
It lies in AX because we are composing a homothety at A and a homothety at X. So it should lie on AX. Let's see by CQ and then cross multiply and
Can you repeat the solve? Someone is asking.
yeah, sure. Okay, so we have so many parallel lines. So we do homothety everywhere. Okay. So we can take a homothety at A which sends BC to D because of the parallel lines. And similarly, we can take a homothety at X, but that will send D to P and Q instead. So what we do is we compose these two homotheties because like we want a relation between BPCQ. Not really, but I mean sort of. Because like, okay. So we need to prove AX is the radical axis of these two circles.
Om, check your name.
Oh yeah, just wait for a second. I couldn't even take the SS.
Hi, sorry. Someone did some stuff. You should just like, it's fine. I'll share my screen again. Yes. Can you hear me and see the screen?
Yes.
Okay. All right. So we need to prove that AX is the radical axis of these two circles. And so A is not really a nice point to prove that because then we'll have to like we only have these 2 points. If we want to do it with A, we'll have to introduce the second intersections of the circle, which there exists a solution using that, but that's not as nice in my opinion. So it's a lot better to consider point Z because then all of these are already really nice points. And so what you need to prove is that Z lies on the radical axis. So the power of Z is equal with respect to both the circles. So do you see why it suffices to show this?
Can you show the problem again? Take a screenshot.
Okay. Done. Okay. So yeah, does everyone see why it suffices to prove this equation?
Yes, because it shows that Z is on the radical axis.
Yes, exactly. So what we do is we compose these two homotheties, and then B goes to P, C goes to Q. So like B goes to D, and then from D to P, because you look at it, take homothetty at X, and then C will go to Q. And the center of this homothetty, if it's like some, this is not Z prime, this is Z prime. If this is the center of the homothetty, then we need to have, first of all, Z prime lies on AX, because, okay, I'll just not draw it, it's fine. Z prime lies on AX because we are composing a homothetty at X with a homothetty at A. So like because of these reasons, A, B, the three centers need to be collinear. So it needs to lie on AX, and also B goes to P and C goes to Q, which means that it needs to lie on BP and CQ, which in this case they're the same line. So it needs to lie on BC as well. Right? So Z is the center of the homothetty. And then Z is the center of the homothetty like this. So now we look at the ratios. Get this. And cross multiply to finish. Does this thing make sense? The whole proof.
Yeah.
Okay, cool. Okay, that took a lot less time than I expected. So,
The first buffer. That's fine.
do you want to do first buffer? Oh, the first buffer. We cannot do the first buffer in 15 minutes. It's
Okay.
yeah. We can do the second buffer, or we can do a different problem. Like the second buffer it's fine as a buffer problem. It's not a problem I would particularly want to talk about in class. So like, okay. There is a different problem. We can do that and keep the buffer problems for buffer purposes. But it might take a bit of time. So like we might have to extend by 10-15 minutes. That's okay.
These problems are numbered. Where are you taking the problems from?
They are just like from a PDF I made for this class. So
Okay.
they're in no particular. I mean, that's the only case in which someone would allow problem 0.6 to happen. Okay. This diagram is hard to draw, but I will try. Yeah, we'll have to do like a bit of head solving because some points will go outside this place and some are just too hard to draw, but nothing too unreasonable. I hope. That's but nice. Sure. Yes.
Maybe drawing the line and pressing shift would work.
Oh, no, they just draw the line and hold it for some time. But
Oh.
what can happen is it can like not pass through these 2 points. If it's too bad, then it will shift slightly. And yeah, that's annoying. Okay. I mean, these lines are okay. They're not that bad. I've done worse. P flat is AD. No.
That's D. Okay, sorry.
Is this P? Okay, prove that IP, BD, and A are all parallel or concurrent. This is not a homothety problem per se, it's more of other normal synthetic geo, but it has one very nice homothety, like one very nice homothety thing. Projective. Okay. That is true. So the original problem where I got this from, it had okay, I see. It's like the original problem was not this. It was about another point K, which is A cap BB, which also lies on this line. But like I just reduced it because you do it's like one line Pascal on ABDE, some hexagon you get from them. So the original problem was projective in that way. Okay. So what do you guys want? Yeah, probably let's just do like some basic angle chasing things first. So this is like not a pure homothety problem. Even it's just a bit of homothety and a lot of angle chase and POP and synthetic stuff. Okay, so you have this. And so yeah, you can chase a lot of angles over here. What do you see? It is because of these two parallel lines. And I mean, obviously, this is just like the alternate angle. And then these two lines are parallel, so you get this angle and this angle for free. So anyway, we can choose a lot of angles. What do you see about this? I'll give you some time. That's fine.
Can we like show that BIPD and AIPE are cyclic?
BIPG. No, what?
BIPD.
BIPD. Where is D? Oh, this is D. Yes. No. I mean that is
Yeah, exactly what I was
not, that is not true.
What about
Ideally, you would want
Yes.
like another point on IP, some nice point like AIE intersection IP. Let it be K, and then you'd want to prove BIKD is cyclic.
okay, we have FGC is similar to ABC.
FGC. FGC is similar to ABC. Is really what? Why?
Because DE is parallel to AB.
Oh, interesting. But why? Oh, yes. No. Sorry, I didn't get it. What? Why is it?
Okay, now I'm doubting myself. What?
We can
No,
also
no,
use
they're
like
not parallel because this angle is different from this angle.
All right, because then it will be red equals blue. Yeah.
Yes. Oh,
can
yeah,
we
what are
also
you saying?
like use arc midpoint stuff?
Arc midpoint stuff, indeed. I mean, no real arc midpoint stuff. Just everything which is marked right now suffices. Like all the marked angles should give you something.
Can we say anything about FPG?
FPG, that is wait, what is we can choose this angle. So I don't know of a solution using this, but we can do it. Like this angle is probably equal to 90 plus c by 2.
90 plus?
90 plus c by 2. Also, I
Like,
never realized I was
Yeah.
doing a C-centric diagram, a C-centric problem. That is so bad. It doesn't feel that bad when you draw the diagram. It's fine. So do you see any cyclic chords with the marked angles alone?
Is APFG cyclic?
APHE.
ABFG.
APHE. What? No. Then we would also have to be cyclic.
Which I didn't get which quadrilateral.
Wait, what? Can you repeat? I didn't hear.
Yeah, which quadrilateral are we talking about? What we are thinking is cyclic. No, like Akshay told some quadrilateral, I couldn't hear it.
Yeah, I couldn't hear it either.
Oh, okay.
AEFI is cyclic.
AEFI is cyclic. Exactly. Yes. No, not I. Oh, yes, indeed I. Okay, so AEFI is cyclic. And so similarly, BIGT is also cyclic. And we want to show AE, VD, and IP concur.
Wait, so you basically want to show P's on the radical axis of these two circles.
Exactly.
Yeah.
So you do radical axis on these two circles and on ABC to get that AE cap BD lies on the radical axis. Rad axis of these two circles. And so yeah, we need to prove P lies on the rad axis. That is correct. And now we need to do very nice things.
We also have IXPY parallelogram, right?
Yes, exactly. We have IXPY parallelogram. We have a lot of parallel lines to work with. So you should think of using those parallel lines for some homothety. It's like this, and this, and this. But yeah.
Wait, it's like it's like the midpoint of IP or something on like does the midpoint of IP lie on AIEF? Or like some special point on IP?
It is a special point in IP, but it's no, it doesn't lie on AIF, AEFA. No, so we don't directly compute the second intersection. We
Okay.
just find another really nice point on IP which works out. And you want to use the parallel lines for some sort of homothety.
Oh, we have C, right?
What do you mean? We have C.
We have C lying on IP.
But C would not lie on AIF.
Why does C lie on IP?
Wait, like AIB is 90 plus C. Similarly, FPG is 90 plus C by 2. So IP, C are collinear.
IPC are collinear. No, that should not be true. That would imply that P is
Okay,
the
it
incenter.
lies on the, yeah, it could lie on the like in center circle,
Yeah,
IFG.
it lies somewhere in the incenter circle. In fact, if it was equal to the incenter, then it would have to be isosceles because like A and B would have to be equal, so these angles wouldn't work out.
Okay.
Yeah, C does not have it. Okay, so now you need to do like the single most direct and I mean somewhat stupid seeming thing to get a homothety.
I have one question.
Yes.
How did we reduce the problem down into showing that a point lies on the radical axis?
We oh, how did we reduce it to saying P lies on the radical axis?
Yeah.
Okay, so we look at these AEFI and these are cyclic because of these two angles being equal,
Yeah.
and similarly BIGD are cyclic.
Yeah.
So look at those two circles and ABC and do radical axis on those things. Then we get AEBD, which is A is radical axis of this circle with ABC, and BD is the symmetric thing. And then these two and the radical axis of these two circles concur. And like the radical axis passes through I.
Can you repeat it? I was.
Yeah. So if we do radical axis on these three circles, then what we get is that AE,
Radical axis.
BD, and the radax of these two things concur. And I clearly lies on the radical axis because I is like literally a common point.
Okay, yeah, I got it. Yeah.
And we do that. And IAP. Oh, interesting. What is this too? IAP is similar to PTO. That would give some interesting results. In particular, it would mean CF is equal to CG.
What would it give? Interesting.
So then that would mean that this angle is equal to the red angle and this angle is equal to the blue angle. So then like the total length is equal. So like this whole angle is equal to this whole angle is what we would get. But how did we get the first part?
Like
Two angles, yes.
AI back. Wait, sorry.
Well, how did we prove this? Yeah, equals 6. Okay. Right. Yes, I see. Okay. So, do you have a finish from here?
I have like just angle just finish, but I will wait for to you to finish.
Okay, sure.
What is L? What is L? I just want to tell.
Oh, L is the radical axis of these two circles.
Oh,
So we need to show that P lies on L. Okay. So I'll give hint.
You said we had to get a seemingly stupid point to get this.
Yes. I mean,
Is,
it's not
is,
stupid. It's just like you'll feel like it was so obvious. You need to do it with the. You need to work with the parallel lines and get on with it.
is it like just midpoint of IP?
No, it's not the midpoint of IP. So, like, you should probably define it not to lie on IP, but with some other property.
What
And
else?
okay, so you need to directly look at how like AD should go to FP. And so look at some specific 2 points and make them map.
AD should go to
AD should go to FP and BE should go to GP.
G
The whole lines.
GP. GP. Okay.
Yes, because that's parallel. Okay, in particular, what we can do is we can make D map to F and E go to G. We take a point.
Midpoint of D.
It's not midpoint of D. D says that D goes to F and E goes to G. Like D will lie somewhere over here.
FG then. Wait, no, I was randomly saying.
It's not midpoint of
Oh,
anything as far as I know. So if we do this, if we look at this point, then it is so nice property. So D will go to F, so like AD will go to XP, and E will go to G, so BE will have to go to the parallel line, which is GP.
Can you tell a bit slow? I couldn't catch up.
Right. Sorry. Okay, so we'll define the point T, which is the center of a homothety, sending D to F.
wait. Can we try from here? I think we can just try from here. Okay.
Yeah.
It shouldn't be hard.
Yeah, I'm not spoiling anything for what you do after this. I'm just saying, so like
T is
AD.
the midpoint of
Okay,
FG.
Mm-hmm.
T. Oh, why? What? No.
I'm asking.
I don't think so. It
No,
probably
like
shouldn't.
how have you defined T?
I have defined T to be the center of a homothety which sends D to F and E to G.
Oh,
We don't
okay.
know what's good about T. It's just that it's what makes the homothety work. That's all.
Okay, got it.
Yeah. I'm just exist here and do some stuff. So what do we get from the homothety? Like what is the point of this whole exercise? Like making parallel lines go to other parallel lines.
So we want to show that the main. No, sorry, no.
No, we don't have anything in particular which we want to show right now. Just want to understand it better. Okay. So you have two lines. So like idea is that I goes to P under this homothety. Because AD will go to XP, will go to FP, and
Oh God.
GP. Yes. That
Okay, wait.
reaction was so perfect. Like, I'll.
Oh my. Okay, yeah.
I want to find Ohm's solution now. I
Yeah,
want to find Ohm's solution now.
yeah, okay. And T lies on the radical axis because this condition just.
Yeah.
Like, first of all, is this solution clear to everyone?
No. Just I'll go to P.
Okay, so T is the center of T is the point satisfying this condition. So like D should go to F and E should go to G. So if we cross multiply, we get TD into TG is equal to TF into T.
PD into G. Okay.
So what does that tell you in view of these circles?
T
Yeah.
radical axis.
Yeah, exactly. So T lies on the radical axis, and now we have like this AD goes to FP, and okay, I'll say it differently in this time. AI goes to FP and BI goes to GP.
Yeah.
under the homothety. So I must go to P, which means that I, T, P are collinear.
Why does AI go to FP?
Because D goes to F and AD is parallel to FP by definition. But by the way, is it? Okay, it's fine.
Yeah, that makes sense. Yeah.
The last part of solving this was very similar to how we solved the previous one.
Indeed, yes. It is similar, so that's sort of the point I was trying to make, that if you have
So ID goes to FP, right?
ID goes to FP, yes.
Okay, yeah.
Yeah, so it is both. So the original, this was, I think it was 11 G5, like it was from G5, not exactly this. It's like slightly modified. So in the other problem, it was not IP, it was KP, where K is this intersection. The K also lies on this. That you can show by Pascal. You can show that Ki and A cap BD are they are collinear by Pascal.
Oh, what are?
Oh, so the original problem was to prove that KP, AE, and BD concur, where these are the tangents.
Okay. Okay.
Okay, but we can get that AE cap BD, AE cap BD, K and I are concurrent. No, what? Collinear. And you can do that by some Pascal. It's like one line Pascal. You take some hexagon with ABD, like AA,
Oh, okay.
and something like this. Yeah, this should work. And then you
Yeah.
get So then you get that point K and I are collinear, and then you need to show P also nice. What was your solution?
No, wait. Let's see.
Okay, so guys, you have like two circles. What do you do with two circles?
No, wait, what? You're doing that?
Just
You don't invert.
Okay.
you take other intersection. That's like,
Okay.
yeah.
Okay.
So consider other intersection. I don't know. Take some name S. Yeah. Then
S. Okay.
yeah.
Q. Q is better.
Q.
What is Which this? two circles
Oh,
are
what
we
is
talking
this
about? Can
naming
you
of?
draw? Yeah.
Wait, which two circles are we talking about?
Yeah. Okay. Shreya, can you draw?
Uh, AEIF and
Okay,
BIG.
okay, okay,
Can you
fine.
draw good
Yeah,
circles, Shreya?
No.
yeah, I guess.
How good circles do you think I would be?
Okay, second one is nice. Erase first one.
Yeah,
Like seriously.
I
This
don't
one
think
just
it's
went
it's
and
just
went on AE.
Like yeah, like so we basically want to show like that intersection should lie on IP.
Yes.
IP.
Yeah, nice. Now wow. Okay. Name it something. Uh,
Q is
okay.
better.
So now you can actually calculate angle FQG, uh,
Okay.
which is basically like
Wait. Let's try. I want to find this
I
one.
mean, it's like not very hard to calculate. So you basically calculate angle IQF 180
Yeah,
minus that,
okay.
which is like
Okay.
IFP. So like A by half plus B by half, and we know that
Okay,
angle.
so is Q the reflection of P?
No, wait. So we know that angle FPG is like 90 minus 90 plus C by half. So
It
QF
is
QFPG is cyclic, and then
cyclic.
by angles you get like IQP is like just collinear, like just angle change. You just finish.
Yeah. Oh,
Wait.
I see, I
Like
see.
if we
No, I
extend
don't see.
IQ, we get that through cyclic
So
quadrature.
you
That's
first
why.
like define
Oh,
Q.
okay, I see, I see, I see, I see,
Yeah,
I see.
you
I see.
define Q, you prove cyclicity, and you say okay, the angles are same, so it just collinear.
Wait. Which cyclicity? Wait. Hold on. What?
But so these things are cyclic, I suppose.
Yes.
Acha. Okay.
Yeah.
Because okay, keep going.
Angles.
Yes, so
Oh.
IQF is
Okay. Yeah.
yeah, it
Yeah.
works.
Oh.
Yes. You don't need it.
Like,
Yeah,
Is there anything more good about this point Q? Like from the diagram, it looks like it's on XY. I don't think it is, but maybe.
mm,
I don't think it is though.
I
and
don't know.
maybe it has good points. Maybe.
But how exactly did we prove D? Okay, wait. Oh,
Where is
right.
it?
Yes. Okay. So to finish from here, what we did got these things by proving ED is perpendicular to CI.
Yes, which is just
Yes.
like Bayesian central lemma or fact
Yes.
five, if you want to call
In
it.
fact, five.
Yeah, fact
It's
five.
chicken foot lemma. Chicken foot lemma.
Oh, sure. No way you say that. No way you say that.
Okay. Stop the recommendation.
Okay, yeah, we can stop recording. Bye, you too.
Stop recording.